All right, thank you very much. Yeah, no worry. I don't want to replace any PhD students, maybe myself, but all other you're safe. Yeah, so I want to talk today about the autonomous optimization of OPV devices. And I work at the Helmholtz Institute in Erlangen, and we work on organic photovoltaic. Why are we working on organic photovoltaic? I think most of you are aware that uh, the, our planet is warming up, and in a speed it's not that nice. So we, as a global society, agree to limit this warming to 1 or 2 degrees Celsius till the end of the century. But like always, the actions we are taking and the actions we have to take to actually achieve our goals are quite different. So we need more renewable energies, and organic solar cells can maybe increase the range of application for photovoltaic, whereas silicon solar cells are not able to compete. For example, organic photovoltaic could be transparent, so you could use it in windows or in greenhouses. And also it's pretty light, so you could use it on your backpack to charge your phone or to charge any wearables you have with you. Yeah, so what's the problem? The problem is we're still lacking behind efficiency and stability compared to the silicon solar cells. So we want to increase those things to be compatible with on the market. The problem here for the organic solar cells is we have a lot of options to choose from. This is, on the one hand, it's a problem because we have a lot of options to choose from. On the other hand, it's good because we still have room for improvement. So if we look at a simple solar cell, you can see it here. Um, we have normally a whole transport layer and an electron transport layer. And for those materials, we have roughly like 10 relevant materials. While for the active layer, we have a lot of more. So in a simple estimation, we have around 10 to the power of 6 different combination to create our solar cell device. But of course, that is not all. We also need to optimize the different layers. And again, for those, we have a lot of parameters which we can choose from. For example, we can influence the layer thickness of our layers. We can use different annealing conditions, or we can change the solvent or add some additives. So in the end, we have a high dimensional space, and we want to find the best solar cell, and we want to find the best solar cell in a fast time, and we don't want to make too many cells. So I don't have the answer for this problem, but I maybe have a way to find a good solar cell in a fast way. So what our group is doing, our group combines automated platforms. Here I have a video of our spinbot. And the spinbot here, you can see we are normally working with glass substrates, which we can put in a carrier, and each carrier can carry 8 substrates. And then this carrier can be transported by the robot. Also, the substrates can be transported individual by the robot. And here you can see our spin coater. And after the robot is done, it can anneal the samples and put it then back in those metal container. And then we can use the stack and transport it to a different station, for example, to an evaporator or to some kind of measurement equipment. So these robots help us to create a lot of cells in a lot of cells, and also we don't need to stay in the lab all the time, but we can focus our work on different things. And now we want to go a step farther. We also want to combine those machines, those robots, with a machine learning algorithm, which then tells us what sample we should produce next in order to maximize our target in an efficient way. So if we combine those two things, we get something like an autonomous lab or a self-driving lab, where we just define the parameters we want to investigate, and then we let the system run by itself and see if it finds a good solar cell. So the spinbot here cannot produce full solar cells, but lucky for me, we have another line, and this line can actually produce full solar cells. So here the line is called line 1, and in this line we have here a pipetting robot which can mix solutions. We also have a spin coater to make thin films. And in the end we have an evaporator which can be loaded by a robot. Maybe you see it in the background over here, to evaporate the top electrode, so we can here produce a full device without any interaction from a human. Also, this line has some characterization. For example, we have an absorption spectrometer, and we also have a solar simulator where we can measure the JV curves. So this machine now can produce the solar cells. It can also characterize the solar cells. So we have the one part of our lab, which is the automated platforms. And now we combine this with an optimizer. And for our case, we chose an Bayesian optimizer. And the goal is to find the optimum of an unknown objective function. And why did we choose a Bayesian optimizer? Bayesian optimizers are made in a way that they use and not that many samples to achieve their goal, because our solar cells, although we have a automated setup, it still takes time and it's expensive to make them. So we don't want to use too many cells to find our best cell. So a quick introduction into Bayesian optimization. We start by building so our objective function is unknown. So in this case, in the plot, it's the dotted line, but normally we don't notice. So we build a surrogate function which is easy and cheap to evaluate, and we build this in a way that it captures our prior belief over the objective function. So for example, if we have some initial data, we can use the initial data to build this. If we have some physical underlying models, we can also include them there. So now we have our surrogate function here, the solid line. Here at some points we already have evaluated the function, so we know where the target is, where the objective is, and now to choose which sample we want to produce next, we build an acquisition function. And this acquisition function is built in a way that it's high, where our surrogate function predicts a good value, and also where our surrogate function, the uncertainty of our surrogate function is high. So you can see here for the sample points, the uncertainty, this is the bluish area, is low because we actually made a cell there, while between the cells, we don't really know what the value of our objective function is. So here the uncertainty is high. So now we choose the point where the acquisition function is max and build this the sample there. So in this so doing this approach, we can exploit and explore. We can have a trade-off between exploration of the parameter space. We build samples where we didn't build a sample yet, so we don't really know how our target value is. And exploitation, we build cells where we think we get some good cells. So we use the cell, we build the cell, and then we feed the result back to the optimizer and update our surrogate function. And then it's an iterative process, so we just repeat it over and over again till we're happy with the result, or when we have a budget, so we just want to do 20 cells and we stop after 20 cells, for example. So if we put this together, our line and our optimizer, and we get something that looks like this. So it starts by a user, and we have a web interface, and the user can there define the target of its experiment. He can define the parameter and the parameter bounds, and also you can create an experiment plan. This experiment plan is basically the steps the machine should do to produce the solar cell. So for example, spin coating, evaporation, measure IV. And this plan is built in a manner that after it's done and finished the measurement, it will create itself again, so we can run it over and over again. So normally we start with an initial data set. We normally use some quasi-random sampling method to get some, so we know a little bit better about our parameter space. And then we feed this initial data set. So it's a solar cell where we measure the efficiency, for example, to a Bayesian optimizer. In our case, we use the scikit-learn implementation, which is it's a well-known Python machine learn package. And then the optimizer will give us some new cells we should produce. Line 1 will then fabricate those cells. It will measure the cells, and then after it measures, it will put the PCE to the optimizer, and then the cycle repeats over and over. So of course we have a database. We store there all the data, for example, the measurement data, the process data, some config data, and also the communication is mainly over the database. So for example, the optimizer runs on a virtual machine, and it just takes a look at the database if there are new sample results, and if there are new sample results, it will take them and write the next samples into the database. So one iteration here takes roughly about 4 hours, depending on the task you're doing. So we were trying to reduce the time of one cycle a little bit, and in order to do so, we used a tool that was developed by some colleagues of mine, and it's basically we can predict the efficiency of the finished solar cells by just looking at the absorption spectra of the active layer. So here, this is from a paper from a colleague of mine published last year ago, if you're more interested in the details. But in short, we have a spectral model. And with this spectral model, we are fitting the absorption spectra. And then we get some features from the absorption spectra. For example, you can see here in the picture, this is an absorption spectra of PM6 Y6. And you can see here, for example, the ordered phase of the Y6 and the amorphous phase of the Y6. So we get here, if we deconvolute it, we get a lot of features. And then we can use these features and try to correlate it with the electronic parameters, in our case, the efficiency. And we do this with a Gaussian progression regression. So we have an initial data set, we measure the absorption, we measure the efficiency, and then we train our GPR on that. So later we can use the trained model on some unknown data and predict the efficiency of the cells from the absorption spectra. So we put this feature in our closed loop, and then it looks like this. So now we start with an initial data set. We actually have to start with an initial data set to train our GPR for the spectral model, while before the Bayesian optimizer could also work without initial data set, but it will take some iterations and more. Yeah, so the initial data set is used to train our spectral model. And then we feed the initial data set to the optimizer. Again, it will give us some new samples, which line 1 will then fabricate. And after the spin coding of the active layer, we measure the absorption. And then with the absorption data, we can feed this into our model and predict the efficiency, which we can then feed back to the optimizer. So instead of taking 4 hours for one iteration, we can reduce this time to roughly 1.5 hours. Of course, our model is not 100% accurate. So in order to prevent any information loss, we still finish the full cells. We measure the efficiency, and then we use the real efficiency to update both the Bayesian optimizer and our GPR model. So the Bayesian optimizer at the start of each iteration, it will check if it has the real PCE of a sample. If it has, it will take this. If it doesn't have the real PCE, it will just take the predicted PCE. So we run this closed loop approach on a ternary composition optimization. We used PM6, Y12, and PCBM in oxaline. And we run two experiments, one with 2 parameters and one with 4 open parameters. For the 2D experiments, we only optimize the ratio of the solution of the different components. So we have 3 components, but the total volume is fixed, so we can reduce it to 2 parameters. The first parameter is here the ratio of the PM6, and the second parameter is the ratio of the 1 acceptor Y12 over the total share of the acceptors. Both of them could vary between 0 and 1 because we wanted to see how it works on the whole parameter space. For the 4D experiments, we also took those two parameters, but we added also the concentration and the spin velocity. So for the 2D experiments, those two were fixed. And the target was quite simple. We just wanted to achieve the best PCE. So if we look at the model performance, on the left side here, you can see the convergence plot. On the x-axis, you have the number of iterations, and on the y-axis, you have the best efficiency that was achieved so far. And we can see that actually for the 2D and for the 4D optimization, we found the best cells after 5 iterations. After that, it didn't increase anymore. But here we have to be a little bit careful. So for this 0th iteration, this is the initial data set. For the 2D experiment, we used only 7 samples as initial data set. While for the 4D, we used 28 samples for the initial data set. So in total, we needed more cells in the 4D optimization to get the best sample. Yeah, on the right side, you can see the model performance. So if you after the run was finished, I run it in a train test split a few times and see if you can predict the efficiency with the parameters I left open. And you can see for the 2D experiments, we have a quite good prediction. And also for the 4D optimization, it's still very good. Yeah, if we now want to look a little bit at what the model, what the framework did, we can here for the 2D optimization, we can look at the objective function. So here on the x-axis, you have the one parameter, the RPM6, and on the y-axis, you have the other parameter. And the points are the samples that we built. So we have here an efficiency, and the heat map is the prediction of our model. So this is for the initial data set, the initial data after the first 7 samples. The objective function looks like this. And then if we increase the number of samples, this is after 3 iterations, after 5 iterations, and finally after 6 iterations, we can see that at the start we used a little bit here of the exploration behavior. We made samples where we don't have too many samples, but in the end, for the last 2 iterations, the algorithm just makes cells where he thought they were good cells because he was quite sure that there in the other region there is nothing. On the right side, you can see the uncertainty of our objective function. So we can see that where we have a lot of points, our uncertainty is quite low, while at the edges where we don't have any points, the uncertainty, of course, increases. Another way to look at those models is we can try to see the influence of one parameter on the target function, and then we get something that is called partial dependence plot. So here on the left side, this is the prediction for the PCE, and here on the left side we have the RPM6. On the right side we have the ratio between the acceptors, and on the other 3 are the different electronic features, JSC, fill factor, and VOC, but just the influence of the PCBM Y12 ratio. So we can see here that for a donor ratio about 1:1, we get the best performing cells, which is kind of expected. And we can also see that the RPM6, so the ratio of the donor, is quite important. If we don't have any acceptor, or if we don't have any donor, we don't get any working cell. So this is our most important parameter here. And then we can see here for the Y12 over the acceptor. So here for 1, we only have Y12 as acceptor, and for 0, we only have PCBM as acceptor. And we can see that if we decrease the Y12 share, we get better performing cells. This is mainly because the JSC increases if we have more Y12 in our cells. while the VOC decreases if we have more Y12 because the PM6 PCBM system can create a higher VOC than the PM6 Y12 system. And for the fill factor, we have an increase, but around 0.9, it doesn't get any better, or it actually gets a little bit worse. So for the fill factor, a little PCBM is in our case actually a little favorable. So if we look at the 4D optimization, it gets harder to plot if you add another dimension, of course, but it's the same plot. So now here we are plotting each target against each other for the objective functions. And you can see on the left top plot, it's the same as for the other ones. We have the RPM6 over the R12 over the acceptors, and we can see a similar picture, which is expected since we use the same materials. If we go now to the concentration and to the spin velocity, we can see that in our case, they actually didn't have quite a big influence on our system. For the concentration, we can see that it increases slightly if we increase the concentration, but for the spin velocity, it's basically a flat line. So it didn't really matter which spin speed we used. We always get a good cell if we use the right RPM, if use the right donor acceptor value. Also here in the plots, if you're confused why it follows here the confidence interval quite good, while it doesn't follow it here, it's because here this is our dominant parameter. If we have a non-working cell because we don't have any PM6 in the cell, for example, we don't get an efficiency no matter how we tune the concentration or the spin velocity. Yeah, so this worked quite well. So we decided to get go one step further, and we didn't want just to optimize for the efficiency, but we also wanted to optimize for the stability, because it would be quite nice if our solar cells don't break after a few minutes. So we rebuilt our optimization loop a little bit. So now we cannot use our prediction of the efficiency, because our prediction from the absorption spectra, because we cannot predict the stability using our absorption spectra. So we have to build full cells. We measure them. Initially, so right after fabrication, we measure it once, so we get an initial efficiency. Then we degrade the cells. In our case, we use an accelerated lifetime setup where we illuminated the cells under 5 suns for, I think, 40 hours. And after degradation, we measured them again, and the PCE after degradation was our second target. So we then put those targets to Chimera. Chimera is a tool as well as the optimizer we used here, which is called Phoenix. Both are developed by the Gustav Brewery Group in Toronto, and it basically uses those two targets and build one target for the optimizer. But also you can use any other function. For example, the most naturally choice would probably be some kind of a weighted sum. Yeah, so now we wanted to so Chimera has a hierarchical order. So the most important target for us was to optimize the efficiency, the stability, and as second target we wanted to optimize the efficiency as well. So if we look here again at the so for this experiment we used a quaternary system, and we can see here that after 9 runs, we found the best cell. And actually, in this case, it was a very trivial multi-objective optimization, because the best cell is the best cell with the initial efficiency also had the best efficiency after the degradation, which is not super unexpected because they're obviously connected with each other. But also you can see here that around run 4 and 5, the optimizer found some cells that had quite a good stability, but the efficiency of the cells wasn't that good. So it tries to improve that further, and after 9 runs, it found here the best cell, which is a PTQ11 Y6 cell with a little bit of PCBM. You can see here on the left side, the cells are ordered by the initial PCE, and on the right side, the cells are ordered by the PCE after the degradation. Yeah, so conclusive, we can say we built an autonomous closed loop optimization, which is able to find the optimum of full organic solar cell devices without any human interaction. Also, our inline prediction helps to reduce the time of one iteration, so we can build more, we can run more iteration in one day. And yeah, for the future, also multi-objective optimization is very interesting. So we can not just find efficient, but also stable solar cells, or maybe also cells that that are really easy to fabricate, or are not or are cheap or something like that. Yeah, I want to say thank you to some of my colleagues, especially Jared Wagner and Christian Berger, which built this amazing lines, and Larry Lure, which made the algorithm for the prediction of the efficiency and also helped me a lot with the ML stuff. Thank you very much for inviting me. Thank you all for listening to this talk, and I'm happily open to answer any questions.